So these two histological images compare muscle in its relaxed state up here and its contracted state. So as we can see, the I band, which is this lighter staining area at the periphery of the sarcomere, is going to shorten, okay? The H zone, right, which is around the M line here, is also going to shorten. Whereas the A band, okay, the area of overlap, remains the same. Okay. Now we're gonna move into the steps of cross-bridge cycling, what happens. And first we're gonna talk about myosin. Myosin, which is the thick filament, the protein of the thick filament. And myosin has two configurations or two forms. It has the high energy form, okay? And the high energy form is when ADP and an inorganic phosphate, right, a phosphate group, is bound onto the myosin ATP binding site. In this configuration, myosin is ready to give energy to the process, and it has a high affinity for actin. Okay, so I want you to think of the high energy state as myosin being attracted to actin. Okay, so in this state, it wants to interact with actin. Whereas in its low energy state or its low energy form, it has an ATP molecule bound. And when the ATP is bound to myosin, it does not want to interact with actin, right? So it does not want to form a connection with actin. And this is going to rely on the hydrolysis of ATP. So in that high energy state, when ATP binds, it's going to get hydrolyzed, and that energy is sort of stored there waiting to be donated to this process, okay? Now, there's a really nice analogy to help you understand what's happening when we have cross-bridge cycling. So if you think about an oar paddle, right? An oar paddle, which you use to row, right? Push water and row a boat or so. The oar paddle can be compared to the cross bridge. The cross bridge, and that's the myosin head that's sticking out, waiting to come in contact with actin. Now, when the myosin head comes in contact with actin, think of that as your oar paddle coming in contact with the water, okay? Now, the power stroke is when myosin drags actin along. And you can think of that as you pushing water behind you with that oar paddle. Okay, that's called a power stroke, that dragging motion where myosin reaches up, grabs onto actin, and drags it along. Okay? Now, when the thin and thick filaments detach, think of that process as you taking your oar paddle out of the water, and you're going to reposition it to a new place to start the cycle again. All right, now myosin head is going to return into its initial position, and that's you bringing your oar paddle to a new position to start that continuous cycle. All right, any questions so far? Okay, so we're really going to take some time to go through the steps of what happens during cross-bridge cycling here. Okay, but I want you to bear in mind the backdrop that the entire sarcomere is shortening as the power stroke happens. So when the power stroke happens, which is where the myosin head or the cross bridge reaches up, grabs onto the actin, which is on top of it, and drags it along, that is called a power stroke. Okay, so the first process here is we have myosin in its high energy form. Remember we said when myosin has ADP and phosphate bound to it, it is in its high energy form. And in that form, it is attracted to actin. It wants to bind to actin. So it's going to reach up and bind to actin. Now bear in mind, this is only in the presence of calcium. Calcium needs to come in, bind to troponin, which causes tropomyosin to move away or uncover those myosin binding sites. So if there is no calcium here, the myosin binding sites will remain blocked. Okay, I'm going to say that again. Calcium needs to be present for this to initiate. It's going to come in, it's going to bind to troponin, and it's going to move or uncover the myosin binding sites on that actin molecule. Actin and myosin are going to come in contact with each other. That's the first step of this process. So the binding site is uncovered, the myosin head reaches up because it's in its high energy state now, and they bind. That inorganic phosphate is released off, and then the power stroke happens. So the releasing of that phosphate off is what causes the power stroke. And again, the power stroke is the head of myosin, now that it's bound onto actin, dragging the actin filament along. Okay, that's your power stroke. The next step here is the ADP is now released off. So myosin has nothing bound to it. Okay, and in this state, it is still tightly bound to actin. And it's going to stay tightly bound to actin unless something else happens. This is step 3. This is called rigor. And rigor means that the muscle is going to stay contracted until the next step happens. If you've ever heard of rigor mortis, right? So that's the stiffening of the muscles after death. So if someone dies holding a cup or sitting in a special position, they're going to stay that way because of this process, right? So rigor is that continuous contraction or binding of actin to myosin. Now this process, myosin needs ATP in order to relax. Remember we said that when ATP is bound to myosin, it's going to transition into its low energy state. This is the state where it doesn't like myosin. It doesn't like actin. It's not attracted to actin, right? So the binding of ATP to that myosin head is going to transition it into its low energy form. And in this form, it is unattracted to actin and they will release. Again, this is why rigor mortis happens, because there's an absence of ATP after death, and so those muscles stay contracted. Now, when that ATP binds to the myosin head, it's going to let go of actin, okay? Then that ATP is going to be hydrolyzed again. It's going to be hydrolyzed into that ADP and the phosphate. Remember we said that's the high energy form. So that phosphate is ready to donate some energy to this process again. That's the high energy form. Actin is going to be attracted, or they're going to be attracted to each other. It's going to have a high affinity here, and they're going to bind again. Okay, the myosin head is going to get into a new position where it stretches out and waits for a new actin.